Say hi to everybody. Say hi to everybody. Say hi. Hey, everybody. This is Mittens. I don't think he wants to be here. What are you doing? What are you doing? All right, get down.
All right. I want to steal your cat.
It's actually my daughter's cat.
I want to steal her cat.
Yeah. You saw it on the New Albany, Floyd County animal shelter. It was a stray somebody turned in. And we've had him now for about a month and a half, I guess. How long have we had him, Samantha? But he's real cute.
You know.
He is very playful. He runs all over the place.
Man, I wish my cat was playful. He just sleeps all day.
Yeah, our other cat, she's 11, and she sleeps a lot, and she's not real thrilled about the little one because he's trying to play with her tail, and she doesn't like it.
Nah.
Let's see.
Am I the only one here?
Nope, I got a few others.
Cool. I didn't see this. Nice.
All right. Let me do this. And we were on this one. Yeah. Except I want to shrink the screen down. Whoop. Go to that one. There we go. All right. Okay. All right. We were doing, oh Lord, I'm behind. 5.6 and I had 5.5 and I had 1.1 question left, number 12. It said solve the following inequality. Okay, so let's see here. I started with the asymptotes, which would be the denominator. So you look at these. So x plus 4, that means that x at -4 would give you a 0, and that's where an asymptote would be. And also at x is equal to +5, because if you put a +5 here, you'd get 0. All right, so that's where your asymptotes would be. So if I were looking at an xy axis, here's the x-axis. So here's a y-axis. 1, 2, 3, 4, and 1, 2, 3, 4, 5. I know there's an asymptote here and here. So I'll just do that part. The zeros, if you set this equal to 0, if you just change as greater than or equal to an equal sign, and solve it for x, you'd multiply both sides by the denominator, which would clear it out. And then all you'd be left with is the numerator. So the numerator is going to give you the zeros, which are your x-intercepts. And so it's going to cross the x-axis, or it's going to at least touch the x-axis at 0. This one will be -9, and this one will be +7. So let's see, 4, 5, 6, 7, 8, 9. There's 0, 5, 6, 7. And then you look at the degree on the x squared, which tells you that the x is equal to 0, you are going to touch there. But on, this is an x to the first and this is an x to the first, both of these. So when it's an odd, you're gonna cross. Okay, so I know that there's going to be a 0 at -9, 0, and 7. And it will touch at 0. It'll cross at -9 and 7. But I don't know if it's going to cross like at 7. Will it cross going like this? Or will it cross going like that? Does it start below the x-axis and the end above it? Or does it start above it and then end below it? That I don't know. I also don't know, does it touch like this? Or does it touch like that? I don't know. I got to figure that part out. So at the moment, this is what I know. Okay. I know I got 2 asymptotes, and then I know that I've got 3 x-intercepts, which divides this thing into 1, 2, 3. Yeah. Yep, that entire. Well, actually, I should do it because in other situations it might be different, so I better do it this way. 3, 4, and what color haven't I used yet? I've used all the light ones. I guess I'll go with gray. 5. Okay, so I've got 5 intervals here. The pink, the green, the purple, the blue, and the gray. And I'm going to have to add another page here. Let's see. Insert another blank slide. Okay. So the pink went from -infinity. Whoops, that's a little thick. There you go. From -infinity to -9. And then the green interval, which was the next one, that one picked up at the -9 and went to the -4. And then the next interval I highlighted in purple went from -4 to 0. And then the next one I did in blue. That one went from 0 to 5. And the last one in lovely gray went from 5 to infinity. And then basically what you have to do is pick one number in each one of those 5 intervals, plug it and chug it to see if the answer comes out positive or negative, because then it'll tell you whether the graph is above the x-axis or below the x-axis. Because basically when you plug and chug, you're looking for the y-coordinate. These are all numbers off the x-axis. So you pick one, you plug it into the function. If it comes out positive, that means the y-coordinate is above the x-axis, either in quadrants 1 or 2. If you plug and chug and it comes out negative, then the y-coordinate is negative, which means the point is down in quadrants 3 or 4, which is below the x-axis. So I just randomly picked some numbers here. What did I pick? I made my little chart here. And I picked my X and then I'd get a Y, my X and then I'd get a Y. Okay, so I picked between negative infinity and negative 9. I went with negative 10. The green between negative 9 and negative 4, I picked, what did I pick? I picked negative 5. Between negative 4 and 0, I went with negative 1. Between 0 and 5, I went with positive 1. And between, oh, shoot. Hang on a second. Did I miss one? Damn it, I sure did. Ah. Boop. Gray should be right here. Hello. Now I need another color. Aw. How about this funky blue color? There we go. Turquoise. There's another interval I missed. Sorry. So there's actually 6 damn intervals. 1, 2, 3, 4, 5, 6. Oh boy. Okay. So I need another one. This is 5 to 7. And then 7 to infinity. Sorry about that. Oops. Come on, pen. All right. So between, what did I pick? Between 5 and 7, I just went with 6. And then between 7 and infinity, I chose 8. Okay. So what you have to do is grab the function, which was, and this is where the fun begins. The function was x squared times 9 plus x times x minus 7 over x plus 4 times x minus 5. And you have to, for every one of these numbers, which I'll highlight in yellow up here, you have to take the negative 10, the negative 5, the negative 1, the 1, the 6, and the 8, and plug them everywhere there is an x in this problem, in this function. Plug and chug and do the math. So like on the first one, for negative 10, it would be negative 10 squared times 9 plus negative 10 times negative 10 minus 7 over negative 10 plus 4 times negative 10 minus 5. Everywhere there was an x, I plugged in negative 10. And you don't even really need to know what the correct number is. You just need to know the sign. So when I look at this and I'm like, okay, if I take a negative 10 and square it, that'll be positive. And then 9 plus negative 10, that would be a negative. And negative 10 minus 7, that would be a negative. And if I take a positive times a negative, my numerator will be a positive number. And then on the denominator, let's see, I need to put this somewhere else. Equals, I have much room here. Okay, then the denominator, negative 10 plus 4, that's a negative number. And negative 10 minus 5, that's a negative. And a negative divided by, or a negative times a negative is also a positive. So I end up with a positive on top over a positive on the bottom, which makes it a positive y, which means when you are in that pink interval, you are above the x-axis. And since I know, let me go back one. Since I know that at negative 9, it's going to cross, then I know that in the next interval, it's going to be below the x-axis. Without plugging and chugging, it automatically has to be below, and it'll approach this asymptote. So I know the next one has to be negative and it'll be below. But if you picked a number, if I plugged in that -5, it's going to come out to be a negative answer. And then I just do the same. When I plugged in the -1, what did I get? Between -4 and 0, I plugged in a -1. I ended up getting a positive answer, so it was above. And then between 0 and 5, I plugged in a +1. Well, I automatically know that this one's going to be above also, because when you're at 0, let me go back. When you're at 0, it's going to touch. And if this is above, then it has to curve like that, and that's above. And so this one, I know it's going to cross somehow like this, and then it's got to, do an asymptote thing here. So I don't know exactly what it looks like, but it's doing something like that. And then when I go to the gray and the turquoise, when I plugged in the 6, I'm now in the gray. When I plugged in the 6, I ended up with a negative answer, so it was below. Hope it's okay that I'm not actually plugging and checking, that you're trusting me that I did the math right. And then on the turquoise, I plugged in an 8, and that came out to be a positive, which is above. And although I really didn't need to do that, because as soon as I found that the gray area was below, and I know it's going to cross right here, this has to be above. So it's got to be like that. Okay, so now, what's the answer though? This is my sketch of my graph, okay? Looks something like this. The original question was, solve the following inequality. So I'm now looking at this picture and I'm going, okay, what was my inequality? Let me come back up here. My inequality, and I'm going to use bright pink this time. My inequality was, where is this function greater than or equal to 0? Where is this above the x-axis? And I went a little crazy over here. Let me fix this. So I don't know, it probably looks like this, something like this. Doot. Okay, so above, I'm going to highlight the graph. All of this is above. All of this is above. And all of this is above. And those intervals were the light pink, the purple, and the blue. So it's from here to here is above. In between here is above. And here is above. Now it does have an equal to, so any point that has that's an intersection point I would include. So I would include this point. This is in the interval, so it's automatically included, and then this point. So my answer that's going to go in this box right here is going to be, the first pink interval goes from -infinity up to the -9 and includes it. That was this right here. Then this is the next interval here, which is in between negative, this was -4 and this was +5, but those are asymptotes, so you can't include them. And since I'm doing multiple intervals, and you'll notice it doesn't say, it says type your answer in interval notation, simplify your answer, use integers or fractions for any numbers in the expression. It doesn't say anything about using commas to separate, so you got to use that union symbol. So now I'm back to this in between. That's going to be from -4 to +5. Union one more, because now I got this guy, which is above the x-axis, and he started at 7, and that's a x-intercept, so include him. 7 to infinity. And that's the actual answer to this whole problem. That was fun. Guys, got any questions on that? Because that was the last example for section 5.5. Nine and yeah, okay. All right, so I'm just gonna shrink that one down and open up this one. All right, this is what we were supposed to do on last week, I think. I'm behind. I think I'm just gonna eat the review day since I'm more behind now. And I actually eliminated something out of this. And if you look at your my math lab homework for 5.6, I removed 2 questions. So, and I'll talk about that when I get there. All right. So, yeah, I'll do it right here. The one that I removed was, we're going to use the theorem for bounds on zeros. And then the estimating, which they don't talk about here. Anything about using bounds, I'm just like, forget it. It's just, there's just so much packed into this section that it's just kind of ridiculous. And this is actually 5.6. Somehow my math lab homework and the PowerPoints that I was provided from Pearson aren't quite matching. So I don't know what happened, but this is 5.6. All right. Oops. Okay, so there they are. We're going to start with number 1, the remainder and the factor theorems. Let's just refresh our memory about what remainders are and what factors are. If I take, I don't know, like the number, I don't know, 9, and I divide that by 2. 2 goes into 9 4 times, that's 8, and there's 1 left over, right? This is before when you first start learning division, and you haven't touched fractions yet or decimals yet, like go back to like the 2nd or 3rd grade, okay? It's long time ago. When you first start learning division, they would say 2 goes into 9 4 times, and then they'd make you put an R up here and then the number 1 because it has a remainder of 1. The remainder is the junk left over. Then when you learn about fractions, you would say the answer is 4 1/2. And then when you learn about decimals, you learn how to add decimal points and zeros and drop them, and you'd get 4.5, right? But the remainder is just the junk left over, okay? Now, since 2 did not divide into 9 evenly, 2 is not a factor of 9. Factors are things that divide in evenly. So 3 does go into 9 3 times. 3 would be called a factor. Over here, the 1 is the remainder. All right? You only get remainders on numbers that are not factors. If it goes in evenly, 3 goes into 9 3 times, that's 9. When you subtract and you get a 0, it divided evenly, that's a factor. Some numbers have a bunch of factors, like the number 12. 1 times 12 equals 12. 2 times 6 equals 12, and 3 times 4 equals 12. So 1 divides into 12 12 times, 12 divides into 12 1 time. So 1 and 12 are factors. 2 divides into 12 6 times, 6 divides into 12 2 times. So 2 and 6 are factors. And same thing with 3 and 4. So the number 12 has 1, 2, 3, 4, 5, 6 different factors. 1, 2, 3, 4, 6, and 12. All right, just to refresh your memory about what remainders and what factors are. All right, so let's move on to the theorem, because you're going to apply this to polynomials, and all of a sudden it looks like a disgusting mess right here. All right, let's say you got 2 functions, f of x and g of x. So remember, they're polynomials. So they could be like, x cubed plus 12x squared minus 3x plus 7. you know, ugly crap like that. So there are two polynomial functions. And if g of x is a polynomial whose degree is greater than 0, then there are unique polynomial functions. And they had to say that the degree is greater than 0 because if g of x had a degree of 0, it would be like 3x to the 0, which is really 3 times 1, which is really 3, which means you're not dividing it by another polynomial. You're dividing it by a constant. So they just have to throw that in there just to make sure that you realize that this whole division thing applies to dividing by a polynomial, not just a number. That's why they say that. Okay, so anyway. So you're dividing. Then there will be a unique polynomial function q of x and r of x such that when you divide, you're going to end up with a remainder. So when I take my two polynomials and I divide it, I'm going to get, and I'll try to use colors here. I got f of x, that's one polynomial. I've got g of x is a different polynomial. When I divide, I get a new polynomial q of x. There may or may not be a remainder. If there is, you will have, need another color for that, the remainder right here. Purple looks too much like pink. Hang on, go with green. But you'll notice that they put it over the g of x, which was in blue. They're making it look like a fraction, just like a minute ago when I took 2, divided into the 9, got 4. Let's see, that would be 8 with a remainder of 1. So it became 4 and 1/2. The 4, and I'm going to color code for you here, the 4 is like the q of x. The 1 is the remainder. This is my remainder. That becomes my numerator. And the 2 is what I was dividing by. That's the g of x. That's right here. I don't know if you can see that, but when I look at this, I have pink plus green over blue. Now they don't put the plus sign right here because those are numbers. It's 4.5. These are polynomials, so they have to put this plus sign in between. You could put the plus sign up here, but 4 plus 1/2 is 4.5. It's the same concept, but you can see it's pink, green over blue. Okay. If, and then they put this or here, they said, or if you were to solve this for just the f of x, so that just the yellow part remains. Okay, so you're coming over here and you're looking at this. It was green over blue, not green, sorry, yellow over blue. They wanted to just be yellow. So if you multiplied both sides by g of x, by the blue stuff, it cancels out on the left, but then it shows up right here, because what you do to one side, you got to do the other. And then it also cancels out there. So when I look at this, I don't know if color's making any sense or not. There's the pink. Then I bring in the blue, and then you still have the remainder over there. They're actually equivalent to each other. So if there is no remainder, then you have just found the polynomial answer, and it's a 0. It's r of x is either going to be the 0 polynomial or a polynomial of degree less than that of g of x, because it'll be a remainder. Now, the remainder theorem says, let f be a polynomial function if f of x is divided by x minus some random number c, then the remainder is actually f of c. And I don't know who figured it out, some old guy, but if you're taking some polynomial function like, I don't know, 3x squared minus 8x plus 2, I'm just making this up, and you divide it by x minus 4. Since it says minus c, in my example, my c is a 4. The remainder will be, try another color here, then the remainder is f of c. So if I were to calculate f of the 4, and I plugged and chugged it into this, you know, and I did 3 times 4 squared minus 8 times 4 plus 2. Yeah, just the numerator, because f, this is my f of x, and I'm dividing it by x minus 4. And if I plug 4 into all these places and do the math, what's 4 squared? That's 16 times 3. 16 times 3 is 16 times 3. What is 16 times 3? 48. Yeah, 48. Woo! 48 minus 32 plus 2, and I do the math, I get 18. 18 would be my remainder, which means I'd have a plus 18 over the x minus 4. That would be this right here, the remainder. Anyway, the remainder theorem will actually calculate what the remainder will be. Now, if the remainder comes out to be 0, which is what the next thing says, let f be a polynomial function, then x minus c is a factor of f of x if and only if, and another way to write that in a math textbook is IFF. That's not a typo. If you ever see IFF, that's like shorthand for if and only if f of c equals 0. So if they ask you to calculate the remainder, right? And you calculate f of c like I did up here, and instead of 18, I got a 0, then that means it divided evenly, which is what I was trying to say back here when I said 3 goes into 9 3 times and you get a 0 right there. If you have a remainder of 0, that means it divided in evenly, and it's actually a factor. And that's what they're saying. It will be a factor of f of x if the remainder is 0. So the remainder theorem just helps you calculate what the remainder would be. If the remainder comes out to be 0, you have found a factor. And the if and only if part, they're basically saying both of these things. If f of c is equal to 0, then that means x minus c is a factor. And
what is c again?
Oh, just some random number. C is some number.
All right, thank you.
And in your homework, they'll ask you to calculate. They'll say, if they're telling you that you're going to divide by x minus, I don't know, 7, and they want to know what's the remainder, you'll calculate f of 7. They'll have to give you c. They're going to have to give you a number. But if you punch that number in and you get a 0, then you know that x minus c is a factor of f of x. And then the flip of that, number 2, is also true. If you're told that x minus c is a factor, then you automatically know if you were to calculate f of c, it should equal 0. That's what the if and only if means. It's got to work both ways. So let's look at an example now. Okay, here's a factor theorem. Use a factor theorem to determine whether the function f of x equals blah, 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 blah has the factor of x minus 1 or x plus 2. So if x minus 1 is a factor, if I were to take the 1, because remember it says x minus c, so just grab the 1. You're just going to grab the 1. 1 is your c in this case. And you're going to plug it here and here and here and see if it comes out to be 0. If it comes out to be 0, then yes, it's a factor. If it comes out to be some other number, then no, it's not a factor. And I think they show that on the next slide for part A. Yep, they plugged it in. They plugged in the 1 here and here and here. And they did the math. 1 cubed is 1 times 2 is 2 minus 1 squared is 1 plus 2 times 1 is 2 minus 3. 2 minus 1 plus 2. There we go. Equals 0. So yes, x minus 1 is a factor of f of x. That's your answer right there. Now, on part B, they wrote x plus 2. Now, keep in mind, the theorem has x minus c. So what you have to do is that x plus 2, you have to write it as x minus a negative 2. There has to be a minus sign right here. That has to match. That has to match. And now I know that c is really the negative 2. And so on this one, you're going to plug in negative 2 here and here and here. That's the way I would do it. They're using synthetic division, which works, but why would I use that when I could just use the factor theorem? So I would plug in, let me switch my pen back to a black pen. I would have 2 times negative 2 cubed minus negative 2 squared plus . So let's see, negative 2 cubed is negative 8 times 2 is negative 16 minus negative 2 squared is positive 4. Positive 2 times a negative 2 is negative 4. And then I get negative 3. That does not equal 0. What does it equal? Negative 20, negative 27. Yeah. So this one's a big old no. That's using the factor theorem. But when I looked at this PowerPoint, for some reason, on part B, they said, you know what? Instead of using the factor theorem, let's just use synthetic division. So I have a question for you all. The class before you took this one, I don't even know what it would be at Ivy Tech anymore. Did you learn synthetic division? Because we have not covered synthetic division yet. Can anybody tell me if you had a class previous to this one that covered synthetic division?
I did synthetic division in junior year of high school. This is my senior year. I did it last year with a different course.
So this is your first math class at Ivy Tech?
Yeah.
Okay. So it was a prerequisite then.
I don't think it was a prerequisite. I think we just covered it as like an extra thing in my last math class.
Right, but if you tested right into college algebra, then whatever it was you had before in high school, I guess.
That's true, yeah.
Has anybody else in this class taken another math class at Ivy Tech before this one? It used to be Math 111, but they don't offer that anymore, so I don't. Or maybe it's Math 043? Does that sound right? 023, 043, do they still have those? Like I said, it's been 6. I'm going on my 7th year from being away from Ivy Tech. Synthetic division isn't hard. It's just, you got to know the method for it. anyway, when they were done with synthetic division, you can see right here is that negative 27 that I found by using the factor theorem. Why you'd want to use synthetic division instead of the factor theorem to answer that particular question, I don't know. No, I think it's okay. But it does say right here, because f of negative 2 equals negative 27, which does not equal 0, conclude from the factor theorem that x plus 2 is not a factor. I don't know. We're going to do some synthetic division in another problem later, but for this example, I would just use the factor theorem. Okay, moving on. I've talked about this before, just kind of refresh your memory. A polynomial function cannot have more real zeros than its degree. So whatever the degree is, if you have like an x, if f of x is equal to x cubed plus, and there's a bunch of crap after this, if the degree is equal to 3, then the number of zeros is 3 or less. It doesn't have to be 3, but it can't be any more than 3.
So a good definition for zeros would be the integers that fit the function.
Say it again.
A good, like, what would a good definition be for zeros? Like a written definition.
Literally, the zeros are the numbers that when you plug them into the function, give you an answer of 0. And they're also your x-intercepts.
All right, thank you.
So if I'm looking for the places where it's going to either touch or cross the x-axis, those are the zeros. Because when you're on the x-axis, y equals 0. So, you know, if you had like 0 is equal to x plus 5 times x minus 4 times x plus 2, because that's an x cubed right there. I can see that my zeros are negative 5. This one would be positive 4. And this one would be negative 2. Those are my zeros, but they're also my x-intercepts. Because if you stick in negative 5 right here, negative 5 plus 5 does give you 0. It causes this 0 here because 0 times whatever would be 0. But there can't be any more than 3. It's possible that there's only 2, and there's possible that there's only 1. And sometimes on quadratics, there's none. I think I've talked about this before. Let's say you had an x squared and your graph looked like this. I call it a floater. That one, even though I know it's an x squared, at most I could have 2 zeros because it's possible for it to do this and cross here and here. But it's also possible for it to do this and sit right on the x-axis. That's only 1. And then it's possible that it has 0. This is 2. This is 1. This is none. 0 zeros. 0 zeros. Okay. And the next concept they want us to talk about is something called Descartes' rule of signs to determine the number of positive and the number of negative real zeros of a polynomial function. All right, so here's Descartes' rule. So again, you got f. That's your polynomial function written in standard form. There's 2 pieces to this. This one right here, which says the number of positive real zeros of f either equals the number of variations in the sign of the non-zero coefficients of f of x, or else equals that number less than an even integer. Yeah, that makes a lot of sense. And then the other one is this one, which says the number of negative real zeros of f either equals the number of variations in the sign of non-zero coefficients of f of negative x, or else equals that number less than an even integer. Okay, let's look at what they mean by all this. Here's their example. All right, so here's my polynomial function right here. This mess. Okay. It is degree 7, right? It's in standard form, which means it's in descending order. And my highest exponent is 7. So that's a degree of 7, which means at most there'll be 7 real zeros. At most. That's what it says. By the number of real zeros theorem, there are at most 7 real zeros. Now, this next part says, since there are 3 variations in the sign of the non-zero coefficients of f of x, which was the part that I circled on the previous page in red, so I'm going to color code it here with red. Okay. When they say 3 variations, okay, how do I explain this? Need another color. Let's go with a purpley color. Okay, 3 variations. You started, when you look from the first term to the second term, there's a minus sign right here. When you go to the next term, there's a plus sign. Then it remains a plus sign, but then it switches to a minus sign. And actually I needed to go from here to here. It's a positive to a negative. That's my first variation because this technically is a positive here. Then you go from a negative to a positive. That is the second variation. This remains positive to positive. So that's not a variation. But then you go positive to negative. That's the third. And then this is negative to negative, so it didn't change. There's my 3 variations in the sign. Does that make sense? And it says of the non-zero coefficients. This went from 3x to the 7th down to a 4x to the 4th. Technically, there'd be a 0x to the 6th and a 0x to the 5th in there, but we never write those because 0 times x is 0. But they throw that in there with the non-zero coefficients. The positive 3 is non-zero. The negative 4 is non-zero. Nobody ever writes those zeros in there anyway. So because there were 3 variations, let me go back a slide to point this out. The number of positive real zeros of f either equals the number of variations in the sign, and we figured out the number of variations was 3, or equals that number 3 less an even integer. The only even integer less than 3 would be a 2. So it's either 3 or it's 3 minus 2, which equals 1. So if I go back, it says, there it is. It says either 3 positive real zeros or 1 positive real zero. Now the next part was in the green. To continue, you have to actually look at f of negative x. So you have to plug in a negative x here, 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 and here, and then simplify it to see how it affects things. What it does is if you have a negative x to the 7th, that's going to be negative x times 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 negative x, which would be a negative x to the 7th, but you're going to take that times this positive 3, which makes it negative 3x to the 7th. It's going to change that sign. For the next one, when you plug in negative x but raise it to the 4th power, that'll still be a positive x to the 4th. It's not going to change that sign. This one becomes a negative. It was positive, it's now negative. This stays negative. The next one, when you plug a negative x in here and cube it, that's going to change it to a negative. When I stick a negative x here and square it, it's still a positive, doesn't change. When I stick a negative x here, it's a negative times a negative, it changes to a positive. And now I have to look at the variations. Let me go back to purple. So, and I'm gonna rewrite this one down here so I can draw on it again. I got negative 3x to the 7th minus 4x to the 4th minus 3x cubed plus 2x squared plus x minus 3. Okay, it starts at negative, stays negative, stays negative, boom, changes to a positive. There's my first variation. Positive is still positive, positive to negative, boom, there's my second variation. There's 2 variations there. That's what it says. There are 2 variations in the sign. So we're going to expect either 2 negative real zeros, or let me go back to the previous slide and look at what I circled in green. The number of negative real zeros is either equals the number of variations, which in that case was 2, or else equals that number less an even integer. 2 minus 2 would be 0. And that's how they get their answers on this one. There are 2 variations in the sign, so we expect either 2 negative real zeros or no negative real zeros. So, as a final statement, they basically say that equivalently, we now know that the graph of f has either 3 positive x-intercepts or 1 positive x-intercept, and 2 negative x-intercepts or no negative x-intercepts. And Descartes is the dude that figured this out. You know, this was back before, you know, social media and the internet, when they had nothing better to do on a Friday night, sit around and play with numbers. All right. Whew. Now we're going to use the rational zeros theorem to list the potential rational zeros of a polynomial function. You're going to love this one. All right. The rational zeros theorem says, let f be a polynomial function of degree 1 or higher of the form, and it's just, they wrote all that out with the a's and stuff where it's got to be in descending order. Okay, where each coefficient is an integer. Remember, integers are positive and negative whole numbers. All right, so each coefficient is an integer. Your coefficients are the numbers in front. Those are your coefficients. If P over Q in lowest terms is a rational zero of P, then sorry, f, then p must be a factor of a sub 0, which is your constant, and q will be a factor of a sub n, which is your leading coefficient. I'm going to try to use highlighters on this one. Go bright. P is going to be, P must be a factor of a sub 0. A sub 0 is the number at the end of your polynomial. And then Q, which is the denominator, Q is going to be a factor of a sub n, which is the leading coefficient. How they figured this out, I don't know. Those are the potentials. So let me make one up here. Let's say I told you that f of x was equal to x cubed plus 4x squared minus 6x plus 9. Okay. So in this situation, my a, which I can't see it because it's invisible, it's right here. It'd be that invisible 1, right? There's an invisible 1 right here. And then at the other end, that's my q, sorry. My p would be this guy. So you're looking for p over q. Now, you need all the factors. The factors of p, the factors of 9 are 1, 3, and 9, right? 1 goes into 9 9 times, 9 goes into 9 1 times, and 3 goes into 9 3 times. So 1, 3, and 9 are my factors of that. The other one, what are the factors of the number 1? Just a 1. So when I'm looking at this, my p's are my numerator and my q are my denominators. My denominator can be 1, but it could be a positive 1 or a negative 1. Because if you took negative 1 times negative 1, that's also a positive 1. So you have to consider negative values as well. My numerator can be any one of the 1, 3, and 9, also positive or negative. It could be a positive or a negative 1. It could be a positive or a negative 3. It could be a positive or a negative 9. So if you were to have a positive 1 over a negative 1, that would give you a negative 1. If you had a negative 1 over a negative 1, that would give you a positive 1. I could sit here all day and do all the variations, but because my denominator is 1 or negative 1, I'm only going to have, you only write it once, I'll either have a 1 or a negative 1. When I look at 3 over 1, whether it's positive or negative, I can have a 3 or a negative 3. And then when I look at the 9s over the 1s, it'll end up either being 9s or negative 9s. So those are all my possibles. Okay, that's just possibilities. Doesn't mean they're all going to work though. And actually, I know they're not all going to work because this function was an x cubed. So at most, 3 of them can work. 3 of them can work, 2 of them can work, or 1 of them can work. Remember, it's an x cubed, so it's going to cross the x-axis at least one place. So I know at least one of them should work. So here they're going to give us example, find the real zeros. Okay, find the real zeros and write it in factored form. So let's start with, well, it's degree 3. So I know there's at most 3 real zeros. And then they used Descartes' rules of signs to figure out that there is 1 positive real zero. They didn't write the original function. Here it is. Copy, paste, there we go. Okay, so for Descartes' rule, I'm looking at the the change, it goes from, remember this is positive, positive to positive, no change. Positive to negative, there's one change, and then it stays negative. There's only one positive real zero because there's only one changes in sign. And then when they plugged in negative x, they got this, and it goes from negative to positive, stays positive, and positive to negative. There were two, right? 2, or 2 minus 0 would be, or sorry, 2 minus 2 would be 0 for no negative zeros. Now, so I've got that much, which means when I look at, and I think they do the next slide here. Yep, okay, let me go back. They then look for the potentials. Okay, your potentials, let me go back to my highlighters. Let's see, I used green for the 6, and I used the pink for the 2 right here. So my denominator is any possible factor of the pink number, and my numerator is any possible factor of the green number, right? So for green, which is 6, my factors are 1, 2, 3, or 6, and it can be positive or negative of any of those. And then my 2, the factors of 2 are 1 and 2, and again, it's any positive or negative of any of those. Okay, when you take into consideration the denominator of 1, so if I take any one of these numbers and put it over a 1, 1 over 1 is 1, so it's either positive or negative 1. 2 over 1 is 2, so it's positive or negative 2. 3 over 1 is 3, so it's positive or negative 3. And 6 over 1 is 6, so it's positive or negative 6. But then I'm going to use the denominator of 2. So now if I take any one of these numbers and put it over 2, 1 over 2 is positive or negative 1/2. 2 over 2, that's just 1. I've already got that right here, so I don't need to list it again. 3 over 2, don't have that, positive or negative 3/2. And then 6 over 2, well, 6 divided by 2 is 3, and I've already got that right here. So there's all my potentials. And that would be, there's 1, 2, 3, 4, 5, 6 of them, but each one is positive or negative. So I have 12 possibilities for this. There are 12 possible zeros. However, back on Descartes' rule, I know that there's only one that's positive and either 2 negatives or no negatives at all. Oh boy. Now, when I look at the next slide, they've already shown what I just shown. There they are. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 1/2, plus or minus 3/2. And at this point, it's simply a case of start looking. It says, from our list of potential rational zeros, we will test 6. I don't know why, they just decided to pick 6 to determine whether it is a 0. Most people start with the number 1. For some reason, they said, let's start with 6. You can start with any number you want. Because f of 6 equaled 780, you know, when you plugged it and chugged it to see if it had a remainder or, yeah, if it equaled 0. If it equals 0, it is a 0, but it didn't. So 6 is not a 0. So now they tested -6 to see if it was a 0. Because f of -6, when they plugged and chugged, they got 0, we automatically know that -6 is a 0. Now, instead of plugging and chugging all 12 numbers, once they found one, you're like, cool, -6 is one of them. So if you have x minus -6, because remember the definition says x minus c. Our c was a -6. So you're subtracting a -6, which means the factor is really x plus 6, which you'll see is right here. And then they said, all right, to figure out the rest of this, either use long division or synthetic division to factor the rest of the function. Since I showed you long division before, synthetic division is a little funky. You take the coefficients of, let me switch to a different color. This was our original function. The coefficients are 2, 11, -7, and -6. If any term is missing, like if that had started with an x to the 4th and then went to an x to the 2nd, you'd have to stick a 0 in here somewhere for 0 x cubes. So if anybody's missing, you got to stick that in there. And then what you're going to do is you're going to take this little division bar and you're going to divide it by the -6 here. That was our factor. Our C is a -6. And this is a little weird, but the first step is always bringing down that first 2. You just bring it down. And then the rest of these steps is always the same. You are going to take this -6. You're going to multiply it times the 2, whatever number is right here. And then you're going to put that number here. -6 times 2 is -12. And then you are going to add. It's like you're going to look at these two numbers and add them together. This 2 right here. 11 and -12 is -1. And then you repeat the same step. You're going to take -6 times the -1 and put it right here. -6 times -6 is +6. And once again, you're going to add these two numbers together. -7 plus 6 is -1. And then right here, when I take -6, once again, and multiply it times -1, boop, we're going to multiply. That's +6. And I should get a 0 here because I already know that the x plus 6 is a factor. It's a 0. It's a factor. So I should have gotten 0 right there. Now, if you look, what color should I use? I'm going to go with yellow highlighter. Okay, if you look at these numbers right here, the 2, the -1, and the -1, right here, 2, that's the coefficient on the x squared. Negative invisible 1, that's the coefficient on the x. And then this -1 right here is that last -1. I've already found the first factor, the x plus 6. And since, purple, since this x, if you divided that out of an x cubed, you're going to get an x squared. So this factor here, or this other factor, has to be the next exponent down from x cubed. It's going to be an x squared. So it'd be a 2x squared minus x minus 1. Okay, so they show all this on the next slide. I was trying to go through it with you. Or did they? No, they didn't. They just said, no. It says now any solution of the equation 2x squared minus x minus 1 equals 0 will be a 0 of f. That equation is called a depressed equation, which I'm sure most of you are also feeling depressed right now watching all this crap. Because any solution to that equation will be a 0. If you're lucky, it'll factor. If you're not, you might have to do the quadratic formula, but this one did factor. They took this 2x squared minus x minus 1, and it factored to be these two factors. So they found the other two zeros. X is this one right here. X would be -1/2, and this one right here, x would be a 1. So we had 3 answers. The previous one was the -6, which I think I did that in a light blue. Right, we had that x is -6, and now we just found the -1/2 and the +1. And if you remember from Descartes' rule, it said there would be one positive and 2 negatives, and there they are. 2 negatives or 0 negatives, but we actually got two negatives. But there's definitely one positive. I found it. And as soon as we found that first -6, I knew there had to be another one, because it's either 2 or none. 1 wasn't an option. But the following, the final answer was they wanted you to, what was it? Find the real zeros and write f in factored form. That was your final step. So my final step in factored form, here it is. So the real zeros were here, and then in factored form, it would look like that. Like I said earlier, this section is jam-packed full of stuff. Here's another example, finding the real zeros. Okay, this one, yep. It's a degree 5, so at most there's 5 zeros. By Descartes' rule of signs, let's see, let's look at the first one. It goes from, this is a positive, goes, let me do it this way, from positive to negative. That's one variation. It switches from negative back to positive. That's a second variation. From positive to negative, there's a third. From negative to positive, there's a fourth. And from positive back to negative, there's a fifth. So it's either going to be 5, 5 minus 2 is 3, or 5 minus 4 is 1. Should be 5, 3, or 1. Is that what they said? Yep. It should be 5, 3, or 1 positive zeros. Then they plugged in the negative zeros. Sorry, I probably should have done that in red, since I had highlighted it in red earlier. When they plug in the negative, it changes the signs, and it goes from negative to negative, 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 0. There, it has no sign variation whatsoever for that, so there are no negative zeros. And then they did the figuring out the potentials. Let's see, green, I'm gonna use green. You got the 36 back here and a, wait, where's the original function? My bad. Well, the sign really doesn't matter. Let me go back to the original function. Where was it? Here it is. You've got the +1 here and the 36, come on, the 36 back here. So my possible numerator factors are anything of the green, and my denominator is of the pink. And of course, the only thing I have here is a number 1. So my denominator can either be a positive or a -1. My numerator can be positive or -1, positive or a -2, positive or a -3. Let's see. Here's 36. The easiest way to make a list of all the factors of 36 is to start with 1 times 36. Then ask yourself, does 2 go into 36? Yep, 18 times. Then go to 3. Does 3 go into 36? Yep, 12. Then go to 4. Does 4 go into 36? Yep, 9. Then go to 5. Did 5 go into 36? No, 5's not a factor. Does 6 go into 36? Yes, 6 times. I turned the corner right there with 6 and 6. So even if I went to 7, it wouldn't go in there, and 8 wouldn't go in there. So I've turned the corner. Here's all my factors. So that's it. Plus or minus 4, plus or minus 6, plus or minus 9, plus or minus 12, plus or minus 18, and plus or minus 36. Is that all of them? 1, 2, 3, 4, 6, 9, 12, 18, 36. Yep. Wow, that's 1, 2, 3, 4, 5, 6, 7, 8, 9 of them over +1 or -1. So that's 18 possibles. Good God. And I'm at 5 minutes and 15. I'm at 5:15 and I'm not done with this yet. Wow. Okay, well, I'm still behind. So I'm going to have to finish this up on Monday. Wow. Okay. I'm just going to end class, I guess. I'm sorry. Maybe I'm explaining it in too much detail. I don't know. But I will have to extend this assignment also. Right now in my math lab, you guys, where's assignments? This is 5-6, so yeah, I just finished 5-5, so you definitely have to get 5-5 done by Sunday, and I'll be extending 5-6, so yep. Any questions?
Thank you.
Bye.